I realized that he also in Brazil. So that prompted us to re-establish our contact, and he was, all the time with me, especially second day when I visited his university. And all I can share with you that he has got remarkable reputation in the department. All senior professors talk very high about him. So it makes all of us proud, HBNI in particular, and of course all of us. So definitely we look forward to listen to your lecture. Now I will request Prof. Datta to introduce you more formally. Over to you.
Yeah. Thank you, Dr. Tyagi.
Good afternoon. Okay, so I welcome you all this 14th monthly HBNI webinar, and this is 11th HBNI alumni webinar. And okay, so this is basically this alumni webinar series is designed to help the present students of HBNI in their placement and to connect with our alumni HBNI. We are very much thankful to our esteemed alumni speaker, Dr. Shyam Sundar, Assistant Professor, Institute of Physics, Federal University of Rio de Janeiro. And Dr. Tyagi has already given his introduction almost. I will formally again introduce him. And I welcome to all the online participants also. There is only one I can see now, but they will join up in also YouTube. YouTube, there will also participants, and there will also people will join. And now I briefly introduce today's speaker, Dr. Shyam Sundar. Dr. Shyam Sundar did his graduation from Bareilly and obtained master degree in physics in 2010 from Banaras Hindu University. He received his PhD from HBNI RR-CAT on understanding superconductivity in binary molybdenum and rhenium. Molybdenum and rhenium alloys in the year 2016. He pursued a postdoctoral position at the Federal University of Rio de Janeiro, Brazil during 2016-2019, where he studied vortex dynamics in high TC iron nictide superconductor. Nictide. PNI. Nictide superconductors. P silent. Iron nictide superconductors. In 2018, he joined Simon Fraser University, Canada for another postdoctoral fellowship where he used the muon spin relaxation technique to study superconductivity and magnetism in quantum materials. In 2022, he joined University of St. Andrews, Scotland for another postdoctoral position where he explored his how uniaxial pressure can tune the electronic and magnetic behavior of quantum materials. He joined as a visiting professor at the Federal University of ABC, UFBPC, Brazil in January 2024. And since August 2025, he has been serving an assistant professor at the Federal University of Rio de Janeiro, Brazil. His research interests focus on investigating quantum materials exhibiting superconductivity, magnetism, topological insulators, and heavy fermion systems, particularly through low temperature measurement in muons spin resonance techniques, spin polarized muons. So with this small introduction, now I invite him for today's lecture, which is on application of spin polarized muons in condensed matter physics research. So I encourage all the participants to actively participate in asking questions and engage with our speakers. So invite the alumni speaker, Dr. Shyam Sundar, to deliver the webinar. Dr. Shyam Sundar, please share your thoughts.
Yeah, thank you very much, Dr. Datta, for the introduction. And can you see my screen, please?
No, sir. Please share.
Is my screen? Can you see my screen? The presentation.
No, so far no.
Okay. Okay. I think I did share, but Yeah, can you see now?
Yes. Yes.
Okay. So as you can see, the title of today's talk is Application of Spin Polarized Muons in Condensed Matter Physics. Before going further and talk about why exactly I chose this topic, and what exactly is the muon spin rotation technique, I would like to just share a brief introduction about where exactly we are located, where is the Federal University of Rio de Janeiro. So basically, Rio de Janeiro is a city in Brazil country, which lies in the South American continent, uh, which is one of the largest country in the Latin American continent here. So basically, Rio de Janeiro is one of the cultural capital of Brazil, whereas the political capital is Brasilia. And UFRJ is first official higher education institution in Brazil since 1920. And Rio is famous for tourist purpose, and it has one of the world's seven wonders, which is called the Christ the Redeemer, which you can see from all over the city. There's a huge statue of Jesus Christ. Um, and of course, they have a beautiful landscape, beaches, mountains for wonderful social life if somebody wants to come and visit Rio de Janeiro. Well, with this brief introduction about the city, I would go now and will give you a brief overview what exactly overall my research interest and what exactly I do. So basically, I study the quantum materials and I synthesize in the lab, and sometimes I do collaborate with other people who can provide a very good quality single crystals. And then I chose basically materials which show magnetism as well as superconductivity for their detailed understanding. And we study these magnetism and superconductivity at low temperature down to millikelvin range and at high magnetic fields. And basically, for those, we used electrical transport measurements, magnetization, heat capacity, thermal expansion, magnetorestriction, or AC susceptibility. These are the lab-based tools we can do in our lab, these experiments. And sometimes, depending on the kind of research we want to do, we do the muon spin relaxation measurement, which require a particle accelerator, as well as the synchrotron-based techniques, which we do collaborate with people from the different synchrotron facilities in the world. So with this brief outline, before starting further, I would like to just acknowledge a few people who helped me throughout my research so far for various purposes. For example, Jeff Sonier and Sarah DeSinger for and MUSR measurements in Canada, Adrian Healer and Ria Stewart from ISIS UK, Rustam Khasnov from PSI Switzerland. These are the MUSR group uh, uh, where we access the MUSR facility. And then the collaborators, you can see in red, the Fuminari Honda, Paglioni, Priscilla Rosa, Heiken Lu, and Marcos Avila. They provide the good quality single crystals for their investigations. And there's some collaborators from Brazil, Luis Kivalra and Angelo Gomez from the same institute where I am. And of course, Dr. M.K. Chattopadhyay and Elishra Chandra from the RRCAT Indore, with whom I do collaborate uh, today as well. And so now with this, I would straight go to the outline of my today's presentation. So I will talk about the muon spin rotation relaxation technique. I'll provide a brief overview about the introduction. And then I'll talk about what are the experimental configuration and the asymmetry spectrum, which we take from this data. And then based on this technique, I will further discuss about the unconventional superconductors and how we get their characteristic length scales, and of course what exactly the time reversal symmetry breaking in these unconventional superconductor. And then I will talk some physics about the superconductivity and magnetism in uranium ditelluride superconductor. And in the last, I will also try to give you a brief overview that how this muon can be useful to study in the chemistry and to study the semiconductor physics and the biological system, and what exactly what kind of information people can get. So although I am not much familiar or experienced in this part, chemistry, semiconductor physics, and biological system. But this is for the information purpose that these systems can also be studied substantially using muon. So why I chose muon? Because it's rarely not well-known technique other than the condensed matter physics, and we can do a lot of different type of study. As I showed you in the previous slide, that I have a broad research interest. So this is basically the MuSR technique. If I can show you, I can cover pretty much all the things which I study. So with this, let's go straight. So what exactly the MuSR is? So MuSR stands for, you can say, muon spin rotation, relaxation, or resonance. So basically, the MuSR, the R stands for pretty much anything which you can use muon for doing your research. So MuSR can also stands for muon spin research. So this acronym MuSR is basically come from NMR, ESR, which are more well-known techniques, and people are more familiar with them in the past. So that's why this MuSR name came into the existence. So it's a collection of method that uses the muon spin to look at a structural and dynamical process in the bulk of a material on an atomic scale. So basically, we use the muon to detect, to study the magnetism, superconductivity, or the different other kinds of phenomena depending on the kind of system we are studying, and to compare it with the other existing techniques. Sorry. To compare with the other existing techniques, for example, the NMR and the neutron scattering, you can see it basically cover the region of the fluctuations, the fluctuation rate, which cannot be covered by NMR and the neutron scattering. So this basically is provide a good technique to fill the gap which cannot be studied using NMR and the neutron scattering. So it's basically the complementary technique for the others. Now, so where are these experiments can be performed? So basically, right now, there are 4 places in the world where these MuSR experiments can be performed. One is in Triumph, Canada, where they have a continuous source, and ISIS, where they have a pulse source, and which is in United Kingdom, in England. And then another is Paul Scherrer Institute, which is in Switzerland, in Zurich, which has a continuous source, and then another is in the Keck laboratory in Japan, which has a pulse source. So basically, the pulse source and the continuous source, they are basically the complementary to each other. They have each have certain limitation, and they complement each other. So these are currently the 4 places where one can do the experiment. So it requires you to submit a research proposal, and the committee judge it, and depending on the science case, they provide you the beam time to do your measurement, just like as the synchrotron facility. Now, what exactly the muon? So before going further, just who doesn't know or know it, studied it a long time ago, I just want to remind that muon is an elementary particle, just like an electron. It doesn't have any internal structure, and it has a spin half similar to electron and proton, but it is heavier than the electron and lighter than the proton. The interesting thing, compared to electron and proton, it is not stable. It has a lifetime of 2.19 or 2.2 microsecond. And so basically, it was first discovered in 1936 by Anderson and Neddermeyer through cosmic radiation, so which comes from the sun. But of course, the flux which comes from the cosmic radiation is not enough to do the experiment. So we need a high flux for doing these measurements, and so we basically have to produce this in the particle accelerator to do it in a more systematic manner. We basically, how do we produce the muon beam? Basically, so we use this graphite target, and basically we bombard the high energy proton on this graphite target, and which generates neutrons and pions. And basically, the pion has a lifetime of 26 nanosecond, and which decay into a muon and the neutrino. And so basically, we take this muon, and we do our experiment. So basically, this muon which comes from this pion decay, which is basically comes through 100% spin polarized manner. Basically, its linear momentum is in one direction and its spin momentum is in the other direction. So the muon spin, it comes with 100% spin polarized, and when it goes into the material, it decay into a positron and neutrino. So basically, this is the positron and the neutrino. We don't care about the neutrino, and we basically detect the positron into the system, and that's how we collect the data, which I will show you further exactly what kind of data looks like and how exactly we do the experiment. So this is just to show you how we get the polarized muon beams. So the interesting thing is here that the muon which we get from this pion decay is 100% polarized. That means when the muon come into our material, we already know what is its direction, and so when it interacts with the internal magnetic field of the material, we can sense that what kind of magnetism is in your system depending on the decay of the muon into a positron. So this is how basically a typical mu-SR beamline look like. So as you can see here, this is basically the experimental station. This is the muon beams comes from. These are the the magnet to focus the muon beam. And here is basically we do the experiment. This is the Helmholtz coil to apply the magnetic field. And these are, you can see, are the positron detectors where we detect the positron after it decay into the muon decay into the material. And we can do these measurements down to the millikelvin range. 20 millikelvin we can achieve. So here we have to connect it through the cryogenic system to achieve the low temperature. So this is the photograph of the muon beamline at Canada Triumph particle accelerator. So basically what happens, so for example, this is the local magnetic moment into your material, and this is the muon. So when the muon go into the material, it start process around the local magnetic field, and within a lifetime of 2.2 microsecond, it decay into a positron, which we detect into a positron. And measuring these positron allow to observe the time evolution of the polarization of the muon ensemble. So basically not one muon, we basically have to collect millions of these decay, millions of muons we need, and then we see their decay, and then we have the time evolution of the polarization of the muon ensemble altogether. So we get the average change in the muon polarization as a function of time, and that basically provides us the details about the magnetism into the system. And this is basically when the positron comes from the muon decay, it comes at several different energies, and so which is basically this angular distribution of the positron is basically governed by this equation, which is basically anisotropic. So as you can see, where this A naught is basically is the asymmetry parameter. So this is 1 if you have the highest energy muon, but since we are connecting the different detectors, and so to detect all those positron with equal probability, this A naught can be less than or equal to 1 by 3, and experimentally we can get this value something around 0.2 to 0.3. We never achieve exactly 1 by 3 because of some experimental limitations. But so this is basically the brief overview about the muon technique. Then how we do exactly the experiment. So basically this is our, suppose this is our sample. The muon comes in this direction. Its muon momentum, spin momentum is in opposite direction. So initially when it comes, it passes through a muon detector and it starts the clock, and then this muon goes into the material and it decay into a positron, which we detect in one either backward or in a forward detector. And then when it detects, this clock stops. So basically then this decay has been counted, and we do these measurements for millions of muons to get the time evolution. And we basically, for each positron decay, we gather them in a time histogram, and then with millions of decay we basically have the time evolution for all these millions of muons decay into that in these detectors. So basically this is radioactive decay. So we can we can see this number of muons into a backward counter defined by this equation, where this tau mu is basically defined the muon lifetime, and this is the local field, and this is the relaxation function. And so similarly for the forward counter, so here we can get the number of muon, the positron detected into forward or backward counter. But if we basically take the total and this subtraction difference of backward and forward divided by the total number of muon counts, and this basically defines the asymmetry, which is the experimental the number which we plot as a function of time. And so this basically is called the asymmetry, and this we plot as a function of time, and then we use several different models to explain this, and we get the information about the data. So basically here in the first top graph, you can see these are the positron counts as a function of time. Since it's a nuclear decay, as you see, this is decreasing as a function of time, and then as you take the difference or divided by total, you get basically the asymmetry, which basically tells about the magnetism into the system. So there are different configuration in which we can do these measurements. This is the longitudinal field configuration. Sorry, this is I missed the zero field, I guess. So basically, this is the longitudinal field. So means we can apply the magnetic field along in the same direction of the muon beam. But this experiment can also be done in a zero field without applying any magnetic field, so that you can detect the local field in the muons at the sample without applying any magnetic field. But basically, this longitudinal field measurement can tell us about the spin dynamics, because if you have a spin fluctuations in your system, you can see if those spin fluctuations are of static nature or of dynamic nature. Basically, so what you do, you can decouple the muon spin from the local static field by applying, increasing this magnetic field value, and you can see how much field you require to decouple the muon spin. And so you can get the fluctuation rate and what is the order of magnitude of that magnetic field which is fluctuating into the system. And so then you can also do the transverse field mu-SR measurement. So basically what you do in this case, you apply the magnetic field in the perpendicular direction of the muon spin. So basically this experiment can be done in several different configuration. So here basically I'm showing you basically we apply the Wien filter, by which we change the muon polarization, and we apply the magnetic field along the beam. So basically the muon spin is this, and the field is in this direction, which are perpendicular to each other. So then this muon spin started rotating around this applied field, and you decay a positron either in these two left and right detectors. So here the positron counts in the backward the left or right counters, you see these oscillations, and when you take the asymmetry, it gives you these oscillations like that, which is decaying as you go higher in time. So basically, if you fit these oscillations, you can exactly tell what is the magnetic field distribution in your sample, how much is the magnetic field you applied, and how much it is distributed in your sample. So with this information, I would like to give you a few examples that how you can study the superconductivity and magnetism using these muons. So before going further, who don't know about superconductivity, just want to remind that superconductivity is a phenomena where you get when you cool down a system, a material, it shows a zero resistivity at a particular temperature. We define as a superconducting transition temperature. And it has another interesting property which shows the perfect diamagnetism, that if you cool your superconducting material below the transition temperature and you apply a small magnetic field, all that magnetic field will be screened. So basically this is known as the Meissner effect. These are the two characteristic features of a superconductor. The further is if you are in the superconducting state and you apply a small field and you keep increasing the magnetic field, initially it got all shielded up to a field called HC1, but when you further apply a magnetic field higher than HC1, the magnetic field starts penetrating into your sample in a very specific manner, which we call basically the mixed state. And if you further increase the field above HC2, the magnetic field start penetrating normally, which is basically the simple paramagnetic state. So we are most interested in the mixed state. So what exactly this mixed state is? So basically in the mixed state, basically you get these vortices. So basically they are the superfluid current here, and then because of this current, you get a magnetic field at the core of these vortices. And so basically they have a very well defined form, usually the hexagonal pattern. So hexagonal lattice. And so if you want to see the structure of the single vortex, so this is the structure of the single vortex. Basically around the periphery you have this super current, and because of the supercurrent you have the magnetic field maximum in the middle of the core of the vortex. But as you go away from this core, your magnetic field start suppressing. So similarly, the superfluid density, which is basically the superfluid the superconducting electron, which we call the Cooper pairs, their density is basically going to zero because the core is normal. And as you go away from this core, you have the superconducting electrons increasing. So basically, if you can see the distribution of this magnetic field into your material, you can basically tell about the penetration depth into the superconductor, which is related with the superconducting electron density. So if you can get their temperature and magnetic field dependence, you can basically tell what is the superconducting gap structure into your of your superconducting materials. You can tell about the pairing symmetry and etc. So basically, I studied a superconductor called lanthanum nickel carbon 2, which is a non-centrosymmetric superconductor, which are very interesting materials because they can show highly exotic and unconventional superconductivity. So lanthanum nickel carbon 2 shows a superconducting transition around 2.7 Kelvin. And why it was interesting, because in 2009, they saw something called time reversal symmetry breaking. The time reversal symmetry breaking, what exactly they saw, they did this zero field MUSR experiment. And when they did, you can see this is measured at 3 Kelvin and at 54 millikelvin, there is a clear difference. So basically, when they did on several temperatures and they analyze this data with this equation, they get this relaxation rate as a function of temperature. They see this relaxation rate is start increasing around exactly at TC and show a order parameter kind of behavior. So basically, this is telling that there is a spontaneous magnetic field appearing at TC, which is basically a signature of time reversal symmetry breaking. So this basically tells you superconductor is not conventional. So then it was important to understand how its gap structure and what is the pairing symmetry in this superconductor looks like. So because of for that, people did some theoretical calculation and they saw that it can only happen when there is an interorbital equal spin pairing on the nickel atoms in these materials. Then it can show this kind of spontaneous magnetization at TC. And in this model, they say depending on the character of these two orbitals which are involved of this nickel atom, this model gives a nodeless two-gap superconducting state associated with two different value of the Cooper pairing. So basically, this Cooper pairing can happen two different orbitals. So this is both spin up, spin triplet, and this is again spin down, which is -1. So this is happening in two different orbitals. So the feature which we are looking for is basically the two nodeless two-gap superconductivity. So for that, to find this experimentally, we plan these MUSR experiments. So we got these single crystals from our collaborator from Fuminari Honda from Japan, and these are the super lanthanum nickel carbon 2 crystals, A-axis oriented. These are the gallium arsenide to suppress the background contribution. So these mounted on a silver plate which doesn't have any relaxation. So it's basically background doesn't have any background. So that's why we doesn't have background contribution into the relaxation. That's why we use this silver uh, uh, plate. So basically what we did, we mount our sample here and we put this muon beam. So basically when this muon comes, its spin, it lies into the plane of this sample, the BC plane of these crystals. And then it decay into a 2.2 microsecond into either this right or left detector. And then we got this asymmetry spectra as a function of time. in a whole temperature range starting from 5 Kelvin down to the 50 millikelvin. So as you can see, 5 Kelvin is in the normal state, which is a paramagnet. You do not see any relaxation here. But when you measure the 50 millikelvin, you see a huge relaxation, which is basically because of the vortex state, as I showed you in the previous slide, which forms a vortex lattice of hexagonal type, so which has a magnetic field distribution. So because of this magnetic field distribution, you see this muon depolarization. So because of this relaxation, we can fit this data and can get the penetration depth. And this is exactly what we did. So we got this penetration depth as a function of field, which clearly shows two different slope. And so two different slope are basically the characteristic of two different superconducting gaps. So we basically confirm that there are two different superconducting gap in length of nickel carbon 2 as it was proposed theoretically. And to get the magnitude of this gap, we plotted this normalized superfluid density as a function of temperature. And by fitting this with the appropriate model, we get the value of the larger gap and the smaller gap value, 1.82 kBTC and 0.77 kBTC. So with this research, we basically resolve the superconducting gap structure in these materials. And now this is one of the research. So basically, this is the lanthanum nickel carbon 2, similar compound called lanthanum nickel gallium 2, which also proposed the same kind of behavior, and was proposed that the superconductivity in these two materials is pretty much of the same type. And so we also resolve the superconducting gap structure in lanthanum nickel gallium 2 compound as well, which is basically compositionally similar to lanthanum nickel carbon 2. Now, another superconductor, which is called the uranium ditelluride, which is one of the rarest superconductor of its type, was recently discovered in 2019 from a group in University of Maryland. So why this was uranium ditelluride was interesting, because before the uranium ditelluride, there are other superconductors called uranium germanium 2, uranium rhodium germanium, and uranium cobalt germanium. They are ferromagnet superconductors. So basically, superconductivity and ferromagnetism, they do not go hand in hand. So where you see the ferromagnetism, it is unlikely to see the superconductivity, because the magnetism destroys the superconductivity. So when people saw superconductivity in this compound, uranium germanium 2, rhodium germanium, and cobalt germanium, it was very much clear that this cannot be of conventional type. And so people were very much interested to study their superconductivity. The interesting thing was that these all materials show ferromagnetic order when they show before showing the superconductivity. And when people discovered the uranium ditelluride, they did not see any magnetic order down to 2 Kelvin, but they saw the ferromagnetic fluctuations. So they are saying that this is the ferromagnetic end member of this series. So when this was discovered in 2019, it was very much important to find out whether this show magnetic ordering at low temperature, below the superconducting function, and the another thing, whether it shows any time reversal symmetry breaking, because this is a ferromagnetic superconductors. They cannot show spin singlet pairing. That means these Cooper pairing can happen spin up and spin down. This is not possible. So either both the spin has to spin up or spin down, which is basically called the spin triplet pairing, and which are supposed to show in these materials time reversal symmetry breaking. So we were basically looking for two different things, whether it shows a ferromagnetic ordering at low temperature, or does it show time reversal symmetry breaking or not. So with these two motivations, we studied this material using zero field MUSR measurement. So these are the samples which mounted on the silver plate, and we did the zero field MUSR measurement. Zero field means, as I said, we do not apply any magnetic field. We place the sample, we put the muon into the sample, and we detect its decay into a positron either in a backward or in a forward counter, and we get the asymmetry, which we plot as a function of time, and we fit this data using appropriate model, where we get this lambda 1 and lambda 2 as the relaxation rate as a function of temperature. So how we find out if there is a magnetic ordering or not using the MUSR measurement? So if you have a magnetic ordering, such as in uranium germanium 2, when you plot this data, like this data asymmetry as a function of time, at a very early time, if you see its behavior, it is supposed to show you very clear oscillations. So these oscillations, basically you can fit the data and can tell exactly how much is a magnetic field associated, and these oscillations is basically the proof that there is a long range magnetic order. And when we did the same measurement in uranium ditelluride, now at 40 millikelvin, we did not see any such oscillation. So basically this tells there is no magnetic ordering in uranium ditelluride down to 40 millikelvin. And when we plot this to see the signature of time reversal symmetry breaking, as I showed you previously, its relaxation rate should show a spontaneous jump around Tc. But when we plot this, the relaxation rate as a function of temperature for uranium ditelluride, we did not see any spontaneous jump in the relaxation rate, rather than this slowly increasing relaxation rate. So this basically tells that there are spin fluctuations into the system, but it does not have I mean, we cannot say for sure if it has time reversal symmetry breaking, because there is a huge spin fluctuations into this system. So basically, we further analyze this temperature dependence of relaxation rate, and we basically tell there are the ferromagnetic fluctuations in this system, which is basically coexisting with the superconducting region into this sample. And basically, this was the very first study on this superconductor, and we found out that these materials single crystals are not of optimal quality. They have uranium vacancies, which are basically changing its magnetic landscape and its superconducting properties. So we further found out that it has a spin freezing because of those uranium vacancies. So we require a more optimal sample where they have very few uranium vacancies. So we basically got another very good quality crystal which shows slightly larger Tc, because the initial superconductor of uranium ditelluride showed the Tc around 1.6 Kelvin, but this is of optimal quality, a better quality crystal, which has RRR, which is residual resistivity ratio, is 200, and it shows a Tc of around 2.01 Kelvin. So in these, when we did the same zero field measurement, we did not see any magnetic relaxation as a function of time. So basically, we can confirm from this measurement that this superconductor does not show any time reversal symmetry breaking. So this basically tells a lot about the superconducting behavior in these materials, in this uranium ditelluride superconductor. Although these are not the complete understanding, the people are still studying these materials with various other techniques to understand the pairing mechanism, as well as the more detailed understanding of the superconductivity in this material. There are so many other systems other than superconductivity you can study. You can study the frustrated magnetic systems, where basically what exactly the frustrated magnetism is. You can basically understand through the structural frustration. Basically, if you have the triangular lattice and you have the antiferromagnetic interaction with this nearest neighbor spin, then if these two are showing this antiferromagnetic exchange interaction, then this third spin would be confused whether it has to be spin down or spin up, because if it is a spin down, it is fine with this, but it will show a ferromagnetic interaction with the other one. So this is basically frustrated spin, and these are called the frustrated magnetic system. So this is basically the structural frustration here, but there are some other systems where they show different types of magnetic frustration, and so we can study the spin dynamics in these kind of systems. And there are plenty of different kind of systems which show the magnetic frustration, and we can study the competing magnetic interaction, and this eventually it can lead to a quantum spin liquid. So basically the quantum spin liquid is the system where you do not see any magnetic ordering down to the lowest temperature or 0 Kelvin theoretically, and their spins are highly entangled, which can be used for some quantum computations technologies which people are working these days. And another field with the muon is called the muonium physics. So as you know, there's a muon, a general experiment when we do in metals. We put a muon into the system, and it start processing around the local magnetic field, and we see a positron. But if your system has low electron densities, for example, the semiconductors or in some insulators, then what happens when your muon go into the system? It basically captures an electron, And then it basically resembles a situation like a proton, where you have a nucleus and only one electron. So it's basically uh, some sort of like a hydrogen like situation. So we can study the muonium behavior into the in materials where we want to study the role of hydrogen. Basically, the role of hydrogen is not very easy to understand because it's very difficult to detect. So people can study the muonium, which basically mimic the same behavior as the hydrogen, and it is lighter than the hydrogen, 9 times smaller than lighter than the hydrogen, basically. So this physics people can study in chemistry. People can study the rate constant, thermal rate constant in different materials. Uh, so this is basically in the hydrogen atom is the lightest of all atoms, arguably one of the most important building blocks in chemistry. The study of the ultralight hydrogen isotope has therefore had a major impact on those fields of physical chemistry that are concerned with understanding the roles of hydrogen and its reactions. So these experiments can be performed very easily with the muon. And chemistry people routinely do these experiments to study the kinetics, the muon, the hydrogen diffusion, activation, and reaction efficiency of the hydrogen in their materials. Another is they can study the local charge transport process in conducting polymers, as well as using the muon uh, MUSR technique, where they can study their diffusion rate as a function of temperature. Another is in the semiconductor physics. So it's, as a trace impurity of atomic hydrogen can have a profound effect on the electronic properties in semiconductor materials, and it can passivate the electrical activity of donors and acceptors in the crystalline semiconductors, dangling bonds in the amorphous semiconductor, and can even display its own electrical activity, all of which are important in the process of semiconductor fabrication. So basically, if you want to understand how the hydrogen gonna affect its properties, you can basically study this using the muon MUSR technique. So basically, where you can see how its relaxation rate is changing as a function of temperature, and you can study the different physics about those semiconducting materials. And initially, basically, this has been very useful in these gallium arsenide system at the very beginning, before people started using it for some time technological purpose. And even people use this technique to study the semiconducting materials. But as I said, this is not exactly my field, and I don't study these materials for this purpose. But this is for the information purpose. So if somebody, one of you, is working on these kind of system and want to explore the how the MUSR can help you, you can basically contact the MUSR people, and then they can help you write a proposal, and can even help do the experiments and analyze the data and to understand what exactly you want to know about the system. And so these are basically, in a nutshell, the MUSR technique and the kind of thing you can do. But this is not very comprehensive. There are a few more things you can do with the MUSR, which I don't have enough time to cover each and every topic. But before completing this part, I just want to say, like any other experimental technique, the MUSR is also have some limitations. So for example, it has the difficulties in identifying the muon site. So basically, when the muon enter into your sample, it doesn't go randomly in any place. So it goes to the highly symmetric site into your sample, but not all not all crystal structures are very easy. And so sometimes it is difficult to find out where your muon site is, where your muon is going into the material. And the limitation to the sample environment, for example, an upper limit of the magnetic field, you cannot apply very large magnetic field. So basically, we do these measurement at 2 Tesla or 3 Tesla, but when you keep applying the high magnetic field, the experiment becomes more and more complicated in a technical aspect. And muon may act as an impurity. So since as a muon is an external particle which going into your system, so basically it can perturb its local environment, and then basically it can alter the intrinsic properties of your system. And so this one has to be cautious. And another thing is it requires a large and expensive particle accelerators. You cannot do these experiments in the lab. That is why you have to submit a research proposal, and the committee judge whether your work is worthy enough to provide you the beam time, because these are very expensive experiments. And somewhat limited time window. As I said, this covers time window between neutron and NMR techniques. So it has a limited time window to see the fluctuations of fluctuation rate into your sample of the magnetism. Well, so if you want to have a more better understanding and what the MUSR can do, whether it can be useful for your topic which you want to study, there is a very excellent book recently published by Stephen Blundell and the other people. You can follow this book. It's a wonderful book. And this completes the presentation. But before completing, I would just like to show you my group where I work. So in the low temperature physics group at the Federal University of Rio de Janeiro, where we are basically 3 professors, Angelo M. Gomez, Luis Welder, and myself. And we have 3 postdoctoral researchers in our lab at the moment, and 2 PhD students, 1 master's student, and 2 undergraduate students currently are working with us. And in terms of the experimental facility, we have a physical property measurement system called PPMS from Quantum Design, where we can measure the AC susceptibility, DC magnetization using VSM, specific heat, and electrometry, which is thermal expansion or magnetic restriction, down to 2 Kelvin and up to 9 Tesla magnetic field. We have another cryostat for calorimetry and the transport measurement from Genis. And we have a benchtop diffractometer for the X-ray diffraction on powder and thin film samples. And we have several furnace for the sample preparation. For example, we have the arc furnaces, we have induction furnace, several tubular furnace, box furnace, glove box, ball milling machine, and sample cutting machine, etc. We have multi-user facilities at our institute, where one can prepare the thin film using the sputtering techniques, and the Squid VSM, which is a multi-user facility, which works down to 7 Tesla, up to 7 Tesla, down to 1.8 Kelvin. We have the multifunctional diffractometer, where you can do even measurements of X-ray diffraction as a function of temperature, which goes down to 12 Kelvin and up to 300 Kelvin. And it can measure the thin films sample as well. And then we also have our own helium liquefier to get the liquid helium. And so currently, I would like to just drag your attention to what are the possible opportunities in Brazil for doing master, PhD, or postdoctoral research work. So basically, FAPERJ is a Rio de Janeiro state funding agency, and FAPESP is the Sao Paulo state funding agency. So they both support the foreign researchers if they want to come here for doing master, PhD, or a postdoctoral research. And of course, you'll have to apply. You have to submit a proposal for your postdoc, and then you get the funding and you can do your postdoc. So initially, they both provide, I think, 3 to 4 years of postdoctoral research. And so the fellowship amount is a little bit different. The FAPESP pays something around 11,000 reais, Brazilian reais, which is something around 2 lakh a month. And the FAPERJ is somewhat less, which is somewhere around 1,50,000 a month. And then you will have CNPK and CAPES, which is basically federal funding agencies. They do support postdoctoral research, but not as much as FAPERJ and FAPESP, and they provide slightly lower funding as well, lower fellowship as well, but they support more masters and PhD students. And then there is another institute called CNPEM, is a Brazilian Center for Research in Energy and Materials, which has a synchrotron radiation source, and it does work on bioscience, biorenewables, and the nanotechnology. So CNPM is a big organization, and they have a huge funding, and they routinely show notifications for a postdoctoral or doctoral positions at these institutions. So if you are, any of you are interested in these things, you can write directly to the professors at Brazilian universities, especially if you want to do for FAPERJ, you have to write uh, professors at Rio de Janeiro State Universities or research institutions, and FAPESP is for in Sao Paulo. And for CNPM, you can go to the website and you can see the information by yourself. And if you want to know any more other information, you can also send me an email, and I can help you with whichever information you would like to have. And with this, I would like to say thank you all. And if you have any question, I would be very happy to answer. Thank you very much. Hello. Hello. Okay. Am I audible? I mean, can you? Uh, hello.
Hello.
Yeah, I can hear you. Okay.
Thank you, Dr. Shyam Sundar, for engaging presentation and giving some details about the opportunities exist in Brazil. And I also share with you we have an alumni group, WhatsApp alumni group, so you can join in that WhatsApp alumni group also. So I will share the link today in your email, so that if you want, you can join, and you can also advise other students that want to give some details in that WhatsApp also group also, that what are the things available in Brazil and where the opportunity exists. That will be good. And if you want, you can share your number in your WhatsApp number. If you think it is possible, that you can share your WhatsApp number also in this YouTube presentation in the below, so that students who want to join, they want to connect with you, they can connect with you.
Okay.
And
Yeah. No problem.
and any question? Okay, so this what you were telling that about the quantum computing, so you have also in your lab made some research about the different quantum computing materials, or and if yes, then in India also is there any such facility available? Still.
So the quantum computation, I don't work directly on quantum computations, but so the materials which are relevant for the quantum computations are only certain type of materials. So basically, I work on the superconductors and the magnetic materials. So there are certain superconducting and magnetic materials which can be useful for the quantum computation in the future, and so they supposed to show certain type of properties, and so one has to know whether they fulfill those criteria. So that is basically we come in, we measure those properties and can reliably tell whether they fall into the category or not. So basically the uranium ditelluride material which I studied was one of the contending member can be used for the quantum computation in the future. And so we were basically investigating the details of its superconducting behavior, whether it can, what it basically show, and then the other people who are working on these quantum computation thing, technological aspect, then they can assess much better. But basically we work on the physics part of those materials, not the technological part as such. But yes, uh, in India, people are working on these systems in quantum materials. There are plenty of groups are working in this system, for example, in TIFR and several IITs. Yeah.
Okay, and then you have any Indian also in your group as a postdoc?
No, not at the moment. We don't know. We do not have any Indian person at the in my group, or I mean, There's one professor. There are, I think, more than one professor in my university, one or two, who are from India, but they arrived here, I think, in 1980s. They're about to retire from the job from here. But there are few Indians, but not many compared to if you see United States and UK. There are relatively very few Indian people here.
Yeah. So
Yeah,
less Indian there in the state. So,
yeah,
but
yeah, but not many Indian students. The one of the thing which is basically people
we have
speak
excellent facility.
Port, I'm sorry.
We have excellent facility, experimental facility, I can see.
Yeah,
So
there's plenty of experimental facilities we have here to do the research. I mean, why a lot of Indian people do not come here? Maybe because we have here the Portuguese language. So the education is in Portuguese language, and if you go in the city, people do not speak English. They everybody speak Portuguese. So language is one of the I'm sorry.
you have to teach in Portuguese.
Yes, I have to teach in Portuguese. Yes. So one has to learn the language. Of course, you can compete for the job in English language, but then afterward you'll have to show your competency in the Portuguese language later on.
That may be the reason for not.
Yeah,
That
for
is
not.
Portuguese is different than Spanish, not Spanish.
I mean, for writing they are, but to speak a little bit different. I mean, it is said that the people who know Spanish they can learn faster Portuguese or the vice versa. But yeah, with both are Latin languages, so they are similar kind of. Yeah.
Okay, thank you very much, and I hope that it will this your talk will be visible in YouTube and it will be seen by many of the students and they will get benefited. And I
Thank you.
also thank Dr. Taggi, Dean HBNI, for introducing you in for BRC alumni webinar. And I will send you the link, and if you wish, you can join the alumni WhatsApp group that I have told already. So thanks
Okay.
to all of you and who have joined the participants. Any question? There is a question from one online
Yes.
participants. So please tell him that. हाँ मैसेज लिख दीजिए अनम्यूट से क्या है म्यूट इट इज म्यूटेड सो अनम्यूट नहीं हो रहा है वो ही इज टू person is to so you would tell him that you unmute तो क्यों वो अनम्यूट नहीं कर पा रहा है अच्छा मेरा भी ऐसा ही हो रहा है
One can write a message in the chat box if that's possible.
That you have sent a message that you send a message with chat box. But you unmute किया है ना? Okay, so neither he is writing.
Yeah, I can't see anything in the message.
Okay. Asi Khandalwal, you want to ask anything, you can ask in the chat box. You can write in the chat box. Because you are muted. Okay. So he is not writing. So see the chat box, anything is not. Okay, there is no question. Yes. Okay, so let us then thank the speaker, Dr. Shyam Sundar, Dr. Shyam Sundar, and thanks our
Thank,
associate dean, Dr. Madhumita, Professor Madhumita here, and I am also Dipanita here, and Dr. Mr. Rohit in IT. Thank you.
yeah. Thank you very much for your support and inviting me for this presentation. It was a great pleasure to connect with you all. Thank you very much. And I look forward to
Whenever you
your
are
email.
please come to HBNI.
Yes, I will.
Come to
Thank you very
HBNI.
much. Yeah. Have a nice evening. Have a nice weekend to you all. Thank you very much. Bye.
Bye.